Yeah, I should have done this a little bit earlier. Yeah, okay, so yeah, so now let me start screen. Sorry about that. Yeah, so yeah, BMC stands for bounded model checking. So bounded model checking is, okay, so even before that, let me say this. Basically, any kind of model checking that you do on programs will always be incomplete, right? Because verifying programs in general is, it's basically undecidable, right? So you cannot ever have an algorithm that will just, like, given a program and some correctness condition will just tell you, okay, this program is correct or this program is wrong. That can never happen, right? So always you'll have to do some sort of a compromise. And this is a theoretical result that was done with Turing. I mean, Turing showed the halting problem was undecidable, and then everybody just reduces things to the halting problem whenever they want to show something is undecidable. So software verification is actually undecidable. So software verification reduces to halting problem, which is undecidable. And this is undecidable by Turing. Yeah, I think it was, yeah, it was Turing who showed this. This is lagging for some reason.
So
yeah.
How is like verification formally defined? What does it mean to verify a
Yeah.
program?
So again, Sarah will probably go over all of these things in much more detail, but very quickly, you have some program. Let's just say it's a C program, right? So instead of giving a formal thing, I'll give you more of a programming oriented definition right now. Is that okay?
Yeah.
Yeah. So, and we'll see that in code, like what this definition translates to in code very explicitly. So program, I mean a C program, and you have some specification, right? Some specification means that some way of saying that this program is correct. Now, this specification, formally, it can be like in various different logics, but in our cases, it will just be a bunch of assert statements. Are you familiar with assert, like in C?
Yeah.
Yeah. So, okay, both of you know C, right? In some amount of C, right?
Yeah.
Yeah. Okay. Sure. So yeah. So the specification is just a bunch of assert statements, right? So what verification means is that this program, C program plus assert statements, none of these asserts should trigger, right? So what we want to do is, given this C program plus assert, we want to pass it through some verification engine or model checker engine, and it will tell you that, okay, asserts don't trigger. And when it tells you that, it should ideally it should give you a proof, but again, like we often have to make a compromise there, or it will give you that asserts do trigger, and in that case it will give you a counter example trace, right? So it will give you like a program trace, like a program sequence of steps and values of variables and so on, which causes one of your asserts in your program to trigger, right? So this is basically the idea behind what this like verification is. Is this definition make sense to you? Does this work for you?
Yeah.
So let's look at some code, because that's sort of the angle from which I wanted to do this. So you can see this code window down here. The font is okay?
Yes.
Yeah. Okay, so we have some really simple code over here. There's just a single main function, and then you have this this if statement. So I'm setting x to this capital X. So this capital X is going to be defined externally, right? So we're going to do dx equal to whatever. And then if small x is equal to, okay, maybe let me make this n just so that, yeah. So if then small x is greater than or less than equal to 0, then we'll just assert 0 here. So assert 0 is always going to fail. We set x to 1 and assert 0. This is just some dummy program, right? But the point is that if I set this capital N to something that is strictly greater than 0, then this program is correct. Otherwise, this is wrong. That is clear to you, right? Both of you?
Yeah.
So in this case, basically, in terms of this sort of pseudo formalism that I said, we have a C program and we have some asserts, and then we are going to pass this C program with asserts to CBMC and have it check it, right? So let's do that. So again, CBMC, and then you pass the program name, which is simple.c in this case. And so you can pass all of your various preprocessor arguments to CBMC itself. So you can pass anything that you would pass to a C preprocessor. CBMC can handle that. Specifically, we're using the dash d to define things. So we are going to do define n equals, let's define it as -1, right? Just so that it causes an error, right? And then if I press enter, yeah, it'll verify this for me and it's telling me that verification fails, right? And it tells me that, okay, verification failed. Why? Because in line number 8 over here, the assertion 0 failed, right? So we have line 8 assertion 0 failed. Assertion 0, it labels these assertions in some order and just saying that, okay, the assertion in line number 8 has failed, this assertion over here, right? So this is the idea. And similarly, if I do n equal to 2, yeah, it says verification successful, right? So this is the idea with any general verification engine, right? You'll have a program with a bunch of asserts in there. I mean, okay, you can have other ways of specifying things. You can have maybe instead of C program, some other programming languages. But the general idea is going to be this, right? You can have more complicated like ways of asserting more complicated properties, but basically let's stick with this sort of a formalism. You have a C program with a bunch of asserts, and then you're going to pass it to your verification tool and it's going to tell you verification successful or verification failed, right? But like I was saying, so this is clear, right? No questions so far?
I actually have a question about this.
Yeah.
So, I mean, how is this different from, I mean, if I just have a bunch of assert statements, uh, oh, so does this like check all possible inputs or?
Yeah, it checks
Like,
all possible inputs. Okay, so we'll see some examples of that maybe, or I can maybe change this code somewhat and make it as that way as well. So for example, if I do this, let's say, so let's just have it as this, and I'll have to add the non-det this thing flag, this non-det static. Right, so it again tells me that verification failed. So right, so imagine if x can be any arbitrary thing, right? So if you look at these formal semantics, then right now x's value is undefined. So of course this can potentially fail, right? It might not fail if you run it, but it can potentially fail. In fact, I think with GCC, if you run it, it will not fail. Let me just check that. Because GCC will initialize this x to 0. Okay, so before we do that, let's make it x less than 0. And yeah, it doesn't fail, right? Yeah, so does that sort of, did I anticipate if, I think I interrupted you before you could complete. Did I anticipate your question correctly and answer it, or did I?
Yeah, that's fine.
Yeah, so basically you're asking with what's the difference between just running the program and letting the asserts fail versus this, right? So that this is sort of the,
right.
Yeah. So I mean, in fact, this has personally bit me. I was like working on something, and it with GCC it was working fine, and then with MinGW it crashed horribly because I was like using some static, some like uninitialized static thing, and then checking, like reading its value before initializing it, right? Of course, you can, if you do say GCC W all, it will give you the warning, which is great. Modern compilers and all. Yeah, see, but the idea is that you can have more complicated things which GCC does not maybe take care of, and with CBMC you can at least get rid of some such bugs before they hit you. And like sir said, they may hit you once your rocket is flying through the atmosphere very fast or something like that. In safety critical things, sometimes there is definitely a point where you can't like go back and debug your code anymore. Like if your code is inside the rocket, or your code is on a machine that is meant to save someone's life or something like that, and then you're really screwed if this thing is has any bug in it, right? So yeah, this is the motivation. We want to check it for all possible inputs, right? So yeah, that is clear, right?
Yeah.
Any other questions? Yeah, so just to say, for any input. Okay, I think I know where this is. Okay, so if there are no more questions, so basically, I said some time back that we cannot actually, like, this general software verification is undecidable, right? So since this guy is doing some software verification, it can't be doing this actual general software verification, right? So it must be doing some sort of, like, there must be some compromise that is going on over here. So with CBMC, the compromise is the following. The compromise is that it is only going to check some, so its check is bounded to error traces of a particular length, right? Some fixed length. So what does that mean? That means that, if you have a program and you want to see that the assert is triggering or not, so the assert can trigger, say, after 10 iterations or 10 statements have been executed. It can trigger after 100 steps. It can trigger after 10,000 steps or a million steps or whatever, right? So your potential counterexample can be as long as possible. But CBMC can only, when you call CBMC, either explicitly or implicitly, and I'll go into more details about those things, how you exactly set that bound. But basically, whenever CBMC is checking this thing, it is assuming that, okay, all of my errors will only happen with traces that are up to 1,000 things, right? So it's only checking traces that say are 1,000 steps long. So if there is an error, so if you say it checks up to 1,000 steps long and your assert doesn't trigger, but it would have triggered if you had checked a particular, say, 1,100 steps long sequence, then CBMC will not be able to tell you that, right? So when CBMC actually says verification successful, it doesn't really it doesn't really give you a guarantee, because for all you know, there may be okay, sometimes it does, but in general you can't really say that, okay, now I've checked everything that can possibly go wrong with this program, because it might just be the case that CBMC has checked only counterexample traces up to 1,000 long, and 1,010 steps later your program would have failed, right? So we'll see some examples of that. Let's see some examples of that. It's better to look at examples than talk a lot of theory, I think. So let's look at this particular example. So do you see this thing? Is the code visible? Yeah. Okay. So what we're doing here is, again, just a single simple loop. We are counting from 0 to n-1, and then 0 to n, actually, because once you exit I will be n, and then what we're asserting is that I is greater than k. So again, n and k will be some constants that will pass in via the command line. Of course, you could have just hardwired n and k into your code, but then I'll have to go and change the code every time and try different things. So that's why I just did it this way. So n and k will be some different constants, and then CBMC is going to try and see if this is true or not, right? So before we pass it to CBMC, intuitively, this is true as long as your k is less than n, right? That's clear to everyone, right?
Yeah.
Yeah. So let's see if that's what we get, right? So, okay. So before even that, I think I should have gone over counterexample traces, but yeah, let's forget about that. Let's just look at this. Sorry. Yeah. Simple loop.c, and let's say d n equals. So let's make n equals, say, 2 and d k equals 4, right? Yeah, so it fails. It says that in line 7, this assertion is failing, which is correct, right? But if I do the other way around, they do n equal to 4 and d equal to 2, it says verification successful, right? So now let's try something, right? So this is here, if you have some particular value of n and k, you know that there's this one counterexample trace that is some specific length long, right? So if you have, say, an n that is actually less than k, then your counterexample trace that shows the assert violating is going to be n steps long, because you'll have to go through this for loop n number of times, right? So if I keep increasing the n, I'll essentially the counterexample that shows me that this program is wrong is going to keep getting longer and longer. And you're going to see that. So if I say, I'll just keep k equals, say, some huge thing, let's say 10,000, so that it's never, So we tried 4. So let's try 8. Yeah. See, let's look at these statements. So this unwinding loop, main.0 and so on, right? So if you look at this over here, when we tried n equal to 4, it actually unwound the loop 4 times, right? So if I do try n equal to, say, 2, it's unwinding the loop 2 times, right? So it's only checking counterexamples of to length 2, right? And when we do n equal to 10 to, or say 10, yeah, it's going to unwind the loop 10 times, right? So again, it's only checking counterexamples of length 10 over here. So we can actually control this via the parameter called this unwind parameter, right? So what we can say is unwind, and let's say that we're going to unwind 10 times. So what this will tell CBMC is that whenever you see a loop, always unwind it up to 10 times, right? So your counterexample trace's length is going to get bounded, because the only way a counterexample trace can grow exponentially is via loops or recursions. And this will, okay, so we'll talk about recursions later, but this will say that for loops, we're going to bound the number of times the same loop can be repeated in a particular counterexample to 10 iterations, right? So again, this gives me verification successful. So what happened here? So if I say n equal to 8, it can find the bug. But now if I say n equal to 20, it cannot find the bug, right?
Sorry, can you repeat this? I didn't get it. Why is it giving a success?
Right. So it's basically this parameter. So this unwind equal to 10, right? So like I said, CBMC basically has this constraint, right? This compromise where it can only check counterexamples up to a certain length, right? Do you understand that? Yeah. So what we're saying, so previously without this parameter, this length of this counterexample, CBMC was sort of deciding on its own. It's not exactly that. I'll say what exactly was happening there. But basically, without this unwind 10 thing, CBMC was doing something and deciding what length counterexamples it needs to check, right? But with unwind 10, what it's going to do is it's going to only check whether this assert will trigger for any path that has 10 times this for loop repeating inside it, right? So what it's doing is it's only checking this thing, like, okay, is there any path in my program where this for loop occurs 10 times and then this assert fails, right?
Oh, okay, yeah.
And this is a fundamental sort of compromise in CBMC. Whenever CBMC is doing any sort of check, there is somewhere hidden behind it this unwind parameter, right? So CBMC cannot ever do any check where there is, say, no unwind parameter, right? Because that, if it was able to actually successfully do that, it would basically disprove your undecidability of the model checking question, right? So there is always this unwind parameter somewhere hidden, and in this case we are explicitly passing it to CBMC. We're telling a CBMC that, okay, it's okay, you only need to check up until length 10, and CBMC will only check up until that particular length for potential errors, right? So any error that happens after a really long program execution that exceeds that particular unwind depth will not be captured over here. So is this clear? Does this make sense?
Yeah. And does this unwind parameter only apply to loops, or like any general C statement? Like if I have 10, or let's say if I have 20 statements and I said unwind to 10, like will it give me that error in that case?
No, it won't. So it only applies to loops, and if you have multiple loops in your program, it will apply to each one of them equally. Okay.
Okay.
Yeah, well, there's a nested loop program where this will be a little bit clearer. But before I go to that, I just want to talk about a few more things, basically. Yeah. It also applies to recursion. So it affects your recursion depth. So it'll limit your recursion depth as well, but it won't apply to general statements at all. Is that okay?
Yeah.
So any other questions here at this point? Is this clear? Am I being able to explain to you guys?
Yeah.
Okay, sure. Right. So now this is basically the idea of the unwind depth. So a few things over here. So one thing that we can do is there is this idea called, so if you look at unwind, and this, I'm just searching the output of double dash help over here. I've just saved it to a file and so on. So look at this. There's this thing called this unwinding assertions, right? So unwinding assertions, what this does is it will generate assertions to check whether this unwind depth was sufficient or not. So if I add it here, right, now it says failure. So notice what's happening here. There are two things that it's checking. One is it that whether the assertion is going to hold or not, and that it actually says that yeah, the search, I'm not getting any counterexample to, like, I'm not getting any path where the assertion fails. But now it's has added automatically this new thing. It's calling an unwinding assertion for loop 0, and it says that this fails, right? So what CBMC can do is, if you set a particular unwind depth, right? So you say it's unwind depth 10. Now, if you want to say prove your program to be correct, like you want an actual formal proof that your program is correct, then you can think of this unwind 10 as a lemma, right? You can think of it as a lemma that says that okay, any error in this program that like, or any execution trace in this program is going to be only like 10, like only going to have this particular loop 10 times in it, right? So you can think of this unwind 10 as saying that okay, any execution of this program is only going to have 10 iterations of this loop in it, right? So this is your lemma, and then using the lemma you have proved your thing, right? So this thing says that okay, assuming that my loop only is going to have 10 iterations, yes, I greater than k, this assertion will never fail, right? This assertion will never trigger. But you still have to prove your lemma, right? So you still have to prove this lemma that says that okay, any like trace in my program is only going to have this loop 10 times. So this extra condition, like this extra proof obligation that you've added in some sense, that this extra thing that you have to prove now, this is called an unwinding assertion, and CBMC can check this for you automatically as well. Again, it's not guaranteed that CBMC will come up with a proof. Maybe it's true that in our program there is like all execution traces are only 10 long, but CBMC may not be able to realize that, but it can at least try, and if it succeeds, then you know that you have a complete proof. But otherwise it fails, and then you have this sort of a situation, right? So then basically, if you use this, you have sort of a few things that you need to decide, right? So you need to sort of decide what your unwind depth is going to be, so how long of unwindings you need to do, and you can use some complexity intuition or any other intuition that you have of your like program to decide that. Then if you add this thing, CBMC will do two checks for it. It will check that okay, if my loops like if every path in this program can go through this loop only this many number of times, then do the asserts trigger. And it says that okay, it does trigger, then you have a counter example. If it says that it doesn't trigger, then that's okay, right? On the other hand, is it even true that all paths in my program will go through these loops only these many times? So there's another part, like another section of your proof. So CBMC will try to prove that as well. So then your proof can fail in like two ways, right? So it can fail because you've actually found a counterexample trace where one of the loops is say 10 long, right? And one of your assets is still triggered, right? So that will basically correspond to the situation where, say, if I put n equal to 5 over here, right? Yeah, so now you see here you have found an actual counterexample where even assuming that, my for loop is only going to happen 10 times, even assuming that this thing triggers, right? So even assuming that this for loop is going to have 10 times, we have a situation where the assert will trigger if we start with n equal to 5. Otherwise, what can happen which is what was happening in the previous situation, was that, okay, assuming that, the for loop will only occur 10 times, we know that the assert won't trigger, but we can't prove that the for loop happens 10 times, right?
Yeah.
Yeah.
And
so now, yeah, go on.
does the same thing work for while loops as well?
Yeah, yes, the same thing works for while loop as well.
Okay.
So I think internally CBMC actually converts all of those loops into, like, okay, I mean, it's not even while loops, it's some other sort of thing, but for now you can sort of think it's internally it converts all of them to one kind of loop in some sense, right? So it, like, CBMC actually doesn't even get to see the difference between for, while, and so on. Like, that is handled at the front end level in some sense, or at the parser level, if you will.
Okay.
Yeah. So just to make another demonstration, if I now put k equals 5 and let's say n equals 8. Yeah, now it is verification successful, and it has proved both of my assertions, right? So this is the case study of this thing. So notice that, like, when your proof fails, you have these two situations when your proof fails, right? In one of those situations, you actually are seeing that the assertion is failing, right? So there you have a concrete counter example, or you can hope to have a concrete counter example to why that describes why your program is incorrect, right? So in this situation, you in some sense know that your program is bugged, because you have found a path which goes through the for loop only 10 times and still triggers the assert. While in this situation, when you don't have sufficient number of unwindings and you aren't able to prove this thing, then you don't even know whether your program is buggy or not. It might still be buggy, it might still not be buggy. Like, it might be that the unwind 10 is actually true. It is true that all paths in your program see this loop only 10 up to 10 times, but CBMC is unable to prove that. That might happen. It might happen that, okay, maybe unwind 10 is not true, but unwind 20 is true, and your program is correct. It might happen that, the program is actually wrong, and you would have found the path if you had set unwind to 10 million, right? So it can be anything in any situation in that scenario. So you can't really do much there other than, like, keep trying larger and larger values of unwind, right? So is this up to this thing clear?
Yeah.
Okay, so I'm making complete sense, right? Yeah. So yeah, okay, so if all of this is clear, then let's try this, right? Let's say k will be this, and let's put this to 10,000, let's say, right? Now it says verification failed. So what's happening here, right? So if we add this unwind 10 thing, of course it's going to tell me success, and then we can go back to that sort of the previous situation that we had. But when we don't put this unwind thing here, what's actually happening? What's CBMC doing, right? So this is the question that we have to, like, sort of think about. So if you look at it, if you look at the output of the CBMC, and I mean, okay, I can only scroll up so far, but essentially, so let me, if I try with 100, maybe then I can at least scroll, right? So if you look at this basically, it starts with, it's unwinding iteration once, unwinding iteration twice, thrice, 4 times, and so on, all the way up till 100 times, right? So it has unwound this thing 100 times, and then it is found this particular trace, right? So it has somehow figured out that it needs to unwind this thing 100 times, right? So how has it done that? So it's nothing very sophisticated at all. See, imagine that you had to pass this unwind parameter, right? Then what would you do? What's the natural thing to do if your situation is this, that you're having a success, but your unwind assertions is, sorry, yeah, so unwinding assertions it is. Yeah, so if you have this sort of situation where your unwinding assertions are false, but you haven't found a counterexample path at all, then in this situation, the natural next thing to try is to try to unwind more, right? So we can sort of imagine writing some code that basically will try to unwind, say start with unwind 10, and then it'll try 11, and it still can't prove it or find a counterexample. Then it'll try 12, and then it'll try 13, and then it'll try 14, and so on, right? So basically what the natural thing to do is basically keep trying larger and larger unwind bounds, and try to see if you can get a counterexample or complete the proof, right? And this is what CBMC is doing internally when you put something like when you don't give any unwind bound to it. So let me just add a couple of zeros over here. Yeah, so if you look at it, it's basically just trying larger and larger and larger unwinding depths, and for each one of them it's trying this thing. So so it starts with, say, unwind depth of, say, something like 1. I think it starts at 1. It'll try to find a counterexample path that sees the loop once and triggers the assert, right? So it'll try a program path, try to find a path that sees the loop once and triggers the assert. It can't find that path, right? So the next thing then it tries is, okay, it tries to prove that the for loop will only run once for any program path. It also can't prove that, right? So now it's confused. It doesn't know what to do. And the next thing that it tries is, okay, now let's try paths of length 2. So is there a path which sees the for loop twice and the assert triggers? No. Then, okay, can we prove that, okay, all paths sees the for loop only twice? Also no. So try longer paths. So in this way, it keeps trying longer and longer and longer and longer paths until you have either it finds an actual counterexample, which is this situation over here. So once it hits a path of this length, then it suddenly can find a program path that sees the loop these many times and that triggers the assertion, right? So it will output that the verification failed. Otherwise, if this thing was actually correct, let's say that k was 100, so it'll again keep trying to find longer and longer and longer and longer and longer paths, right? But now what happens is that once it has found these many number of paths, see, since this thing is correct, the assert will never be triggered. We know that, right? So even with 100,000 long a path which sees this for loop 100,000 number of times, it can't, like, it hasn't found a path which will trigger the assert. So it can't say verification failed. But now it can actually prove that, okay, all the paths in my program will see this for loop up to 100,000 number of times. There's no path in my program that is going to see this particular for loop repeated 100,001 times, right? So now it knows that, okay, my unwinding assertion is correct. So the second part of this proof is correct, and it says verification successful, right? So does this make sense?
Yeah.
Yeah. So this is what CBMC is doing. So this is basically what this is just what CBMC does, and everything else over here in the help and so on is just some extra stuff that is around this thing, right? Okay.
But
yeah,
in this particular case, this is only, I mean, if we don't specify the values of n and k, then how long will it go before it
it'll
stops?
keep running. It'll keep running. So in fact, I think I don't have a program like that, but let's quickly write something like an infinite loop, right? So let's say, so let's just say while true. Okay, I think true is not there in C now. Yeah. So let's just do this just so that we have some statement inside there. Let's have some int I equals 0, and we'll say that I plus plus inside here, right? And let's say that we assert false over here, right? Good question. Does this assert ever trigger, right? That's a really good question. But if you pass this to so we don't have any defines over here, so let's just pass this to CBMC and what happens. Oh, okay. Why is it saying what?
It has to return, I guess, return something.
Yeah, that would be one error, but I think there's something else going on here as well.
Oh, I think it's assert.h.
All right. Yeah, that was dumb. Yeah. Now this is going to keep happening. So that's the so when you don't pass an unwind depth to CBMC, that is sort of the other compromise that you or the other side of the compromise that you see. So now CBMC has no way of knowing like when it has searched long enough paths, right? So it will keep searching paths, and it may forever keep searching paths. You won't ever know um there is no way for you to know when it will like stop searching paths in general. Of course, looking at this program, you know that this is an infinite loop, so it will not stop, right? So in fact, CBMC can never prove that this program is correct, because its entire strategy is based on saying that, okay, I'll bound the number of iterations each loop is happening. Well, this entire program, the point of this program is that this while loop is going to occur infinitely many number of times, right? So before things begin to crash, let me just stop this. Yeah, so does this answer your doubt?
Yeah.
Yeah, so it will basically just keep happening. In fact, you can do something like, take your favorite unsolved number theory open problem and write a while loop that will terminate if that problem is true, right? That is that is an exercise that you can do, and then pass it to CBMC, because if CBMC could do that, then your number theory would have just been solved. Right. So, okay. So is this program all fine? Up until now, no questions. Yeah. So now let's look at something. So I'm just going to backtrack back to this simple.c, because I forgot to show you the counterexample traces part. So if I do simple.c and right. Yeah. So let's keep this non-deterministic. Let's not add that. So let's say non-get static. This verification failed, right? So this doesn't really help us as developers much, because it doesn't really give us where how exactly this error is happening, right? I mean, it says that it's happening in line 8, but you know that usually when you see an assertion is failing, you then step into a debugger and try to recreate that. So what would be nice is if it actually printed out this particular program path that is causing this assertion to trigger, right? So we can do that by passing --trace, and now it is printing out this path. But it's, I mean, okay, maybe you can make sense of this output, but I usually I can't really make sense of an output like this, because like this just feels weird and complicated to be. It doesn't give you the program statements. It doesn't show you which function you're in. So let's add some extra information to this trace printout, and then we'll look at it like seriously. So let me go down over here and see that there is a bunch of things you can like add to the trace print. So first thing is we'll add trace show function calls. This is especially, in fact, this is crucial for recursive code. Another thing that would be nice is trace show code. And now you can see that whenever it has some value, it is printing out this value in binary in parentheses. And this might be useful in some cases, but I'll just switch it over to hexadecimal. So trace hex, right? Yeah, and now it's prints out something that is a little bit more readable. So let's go back to the program and follow what's going on. It's in line 5. So it says line 5 over here, right? So in line 5, thread 0 is like, we're not doing multi-threaded, so let's not worry about that. So line 5 in function main. So even before that, look at that, there is a function call that is happening over here. And after the function call, we end up in line 5 in function main. But this is what we're executing. And what this is doing is it's doing an assignment, right? So each state in your path that CBMC will print out is going to have exactly one assignment as a part of it, right? So what CBMC will essentially give you is a sequence of assignments that happen at various points in your program. So what this is saying is that, okay, in line 5, this statement was executing and it's adding this signed thing here because I think the parser is automatically adding this thing. And this is the assignment that it's doing. So it's some random integer value, right? And then it's going to go to line 7 and it's going to assign x to 1, right? So it was here assigned x to some non-deterministic negative value or some random negative value. And then over here, it assigned x to 1. And then now we have assertion being violated right after that, right, in line 8. So this is how you can get counterexample traces out of it and interpret that. So let's also do this for the simple loop. So let's just say simple loop, and we'll say d, let's say n is going to be 2 and dk is going to be 4, right? Yeah. Okay. So it's going to give you this particular counterexample trace, right? So again, at line 5, it's setting I to 0. I think we didn't have, yeah, we do have non-dead static. So, but it's still it just shows this initial value of I to be 0. And then we are setting I equal to 0 in line 6 inside the loop. Then we're doing I equal to I plus 1 once. So we are doing the loop again. And again, I equal to I plus 1 again twice. So now I get set to 1 and then 2. And then we are seeing the assertion pilot, right? Okay, so this counterexample traces are fairly readable. Does this make sense to you guys?
Yes.
Questions? Any questions? No questions? Okay. Is everything clear?
Yeah.
Okay. All right. So let's quickly look at two more, somewhat complex, two more different examples, and then we'll go to the example that Sir had in class, because I think it's good that we covered that here. So this is a nested loop example, and okay, I mean, I'm just going to skip this. I'm just going to describe this verbally. If you want, I can do this more, but then you'll have to allow me more time, basically. So this is just a nested loop. It behaves exactly like in the previous loop. The important thing is that if you put an unwind depth, it'll apply to all of these things, right? So it'll apply to, so if you say put an unwind depth equal to 2, it'll apply to all 3 of your for loops, and you'll actually get this statement executed basically 8 times, right? So this loop can happen, like you can see this loop twice in your path. You can see this loop twice in your path for every time you entered the loop, and you can see this loop twice in your path for every time you entered the loop. So in total, this entire nested structure can execute 8 times, right? So when you put some double dash unwind, that's basically how it is interpreted by CBMC. Every time you enter the loop, that particular, you can stay in that particular loop, or you can iterate in that particular loop, unwind number of times. And you can do things like, specify different unwind lengths for different loops in your program, but you can read the docs for that. I'm not going to show that here. So do you want me to show this, like demo this, or this is okay?
I think it's okay. Maybe you can like share this and we can maybe try it on our own.
Yeah, that I'll do. That will definitely do. I'll put this on. Yeah. Okay, so the next one is this. I'll demonstrate. This is the simple recursive program. So yeah, so let's look at this program. So this recursion, what this does is, if k is 0, then you return 0. Otherwise, we're going to just print k. This is just, I'm just using a bunch of temporary variables because it makes this trace easier to read. Because you'll get more statements and you'll get more assignments and so on in various different statements. So what this is just doing is it's calculating a rec of k minus 1, adding 1 to it, and then returning it, right? So this is a recursive way to calculate, like, this is basically a recursive function that does a bunch of steps to return k back to you, right? So again, we are doing the same thing. We're going to recursively and recurse n number of times, and then the assert is basically, is the return thing greater than k or not? So it's essentially the same sort of setup as the loop thing. So let's see what happens there. Yeah, so it says the assertion is failed, right? So I recursed twice. And let's look at the trace. So the trace is a fair bit longer. And let's see whether we can make sense of it, right? So initially, of course, we have a function called main, and we are in this line 14 of main. We set I to 0. So this setting I to 0 is because it splits things like int I equal to something to two parts, right? It'll split it to the declaration and then the definition, right? So the declaration happens and then the function call happens. We are calling it with 2 because n was 2 here, and we set k equal to 2 at the, this is setting the formal argument of the call. Then inside over here we have the print statement, so it prints out this thing, and then we're declaring t, so t is getting set to 0, and then we're going to say that, okay, we're going to do another function call. This is the recursive call, this time with k equal to 1, and then again t is going to set to 0, and then we're going to do a third recursive call with k equal to 0, and then this one returns immediately because line number 5, right? And then we're setting this t, so when it returns, we're back in this rec1 call, and then we're setting this t from the return value. So we're setting t equal to 0, and we're setting ret equal to initialize to 0, set it to t plus 1, so ret becomes 1, and then again we return from rec, right? So then inside rec 2, this will be the second or the first depth call over here. This will give you, your t will be set equal to the return value that you had here. So this was 1, so it will be set to 1, and then your final return will be 0. Sorry, it will be initialized to 0, and then you set that to t plus 1, 2, and then you return that. And then you set that to I, so I is 2. That is back inside of main right now. You're still in line 14 in main. And then you see that the assertion is validated in line 15. So this is clear, right?
Yeah.
Yeah. Similar to before, you can, okay, just before, so you can do, like, if I set k equal to 2 and equal to 4, it will be verified, right? So similar to before, we can actually have a limit to the number of unwindings. So I can say at n equal to 1000, 100, and k equal to something huge. And then I can say I'll unwind only up to 10 times. Right? And it says verification successful, right? Now, here's a really important caveat for using CBMC. If I now add the unwinding assertions, it still says verification is successful. The reason is that unwinding assertions actually only work for loops. They don't work for recursion. So with CBMC actually does not have any way of figuring out with recursions, like whether or not the unwinding assertions are like successful or not, right? Maybe it internally has some ways, but at least you cannot get it to print out that thing, right? So unwinding assertions, this particular unwinding assertions flag and combining it with passing a particular specific unwind value, this works only for loops. It doesn't work for recursions, right? So if you have a recursive program and it says success, you really don't know anything, because you'll have to basically separately on your own prove that, okay, the recursive depth that it has used, that CBMC has used, is actually enough to prove this thing or not. CBMC cannot do that for you automatically. So this is another caveat of using CBMC, or I mean, one of the limitations of this is a thing. And it is, I mean, a compromise. I think recursions are much more complicated, and you can have like a lot more weird sort of behavior over there. So being able to say that, a particular recursion is bounded and automatically checking that is fairly difficult, right? So no questions about recursions, or is it?
But
okay?
at least theoretically, there is, I mean, every recursion can be converted to a loop, right?
Yeah. So if you have a single recursive function, then it can. But are you sure that if you have to say 5, 6 different recursive functions all calling each other, then that also can be always be converted to a loop?
I'm not sure. I'm just guessing, but yeah.
Yeah. See, I'll have to also think about that. See, yes, I'm definitely sure that with one this thing you can always do it. Okay, I mean, you can always just simulate the stack in the loop. So that you can always do. So in that
Yeah.
sense, you can convert it into a loop. But then remember, you're also simulating the stack. So there is an added data structure that you're requiring, right? So your loop doesn't have say, so each state in your loop doesn't have, say, 5, 6 or finite number of variables. It has some array or some stack in there, right? So
Hmm.
so that can allow you to like make more complicated things.
Yeah.
Yeah, in general, I think though, yeah. Yeah, but I think, I mean, I guess things like putting like figuring out recursive bounds like automatically and stuff, I think those sort of things can be done. But I just think that this is not implemented in this particular thing here, right?
Okay.
Yeah, but don't quote me on that. Yeah. So there is this course called like infinite state verification, where if I remember correctly, I think I did see a few things where you can figure out the bounds for stack-based machines. But again, then there's the caveat that if you have to convert your program to stack-based machines, then all the states of your individual function calls have to be finite. So yeah, there's some stuff there which we can talk about later on, I guess. So is there any other questions? Okay, I think, yeah. I'm not sure if I'm saying something wrong here, actually. But I'll come back to you about this, I guess. If Dhruv was here, I think maybe he would have known this. Any other questions? Hello?
I have one unrelated question. I mean,
Yeah.
so it says like there is something called SAT checker inconsistent, instances unsatisfiable.
Yeah.
Yeah,
So,
so like what is that?
right. So, I think sir will go into a lot of details about this, but very briefly, what this does is basically it will create a general symbolic sort of representation of a general 10 length path in your program, let's say. So you have a program, and if you can imagine that, you can sort of say that, okay, a 10 length path can, at state number 1, you'll be here, and the variable value is going to be, say, x, y, and z. So in state number 2, you'll be here, and the variable values in that state is going to be 1 plus the variable values in the previous state, right? So in that way, you can symbolically create a representation of a 10 length path, right? So for example, with this simple loop program that we were looking at, so this simple loop program that we're looking at, if we say use an unwinding length of, say, 5, then we have 5 iterations of this loop, and we can say that, okay, there are 5 copies of this I variable for I at iteration 1, I at iteration 2, and up to I at iteration 5. We'll say that, okay, I at iteration 1 is actually 0 because we are setting I equal to 0 there. We're also going to say that, okay, I at iteration 2 is going to be 1 plus I at iteration 1. I at iteration 3 is going to be 1 plus I at iteration 2, and so on. So that will encode this statement. And then you can say something like you can add another condition that, okay, I at iteration 1 is less than n, I at iteration 2 is less than n, and so on. Right? So you can add that sort of a condition to everything. So then you have essentially encoded this 5 length path, or 5 iterations of this for loop into a formula, right? So does that sort of make sense? If not, then things will go. Sir will go over more details about this, right? So then this SAT solver is basically something called a satisfiability solver. This formula is just going to be some Boolean formula, because everything in your program can be represented in binary and so on. So it's basically going to take this Boolean formula and pass it to a program that can check arbitrarily long Boolean formulas, right? So that is your SAT checker. And if it says unsatisfiable, then that means that this long Boolean formula that you have doesn't have any like doesn't take this long Boolean formula. If it has an actual satisfiable, like if it has some particular values of variables for which this formula holds true, then that would mean that your assert has triggered. So if it is unsatisfiable, then that means that your assert has not triggered. So does that at least intuitively make some sense to you? So it's basically like this. You take your program plus a path length, and then somehow encode that into a formula. So you encode that into a formula. So what this means is that so this formula has got variables like x at 0, x at, so at 0 means at iteration 0, at iteration 1, and so on. So if you have this formula with these variables and various relations that encode the statements, then if you can find values of x, these x at various points in your program that satisfies this formula, if you can find x's, find satisfying x's, then you have a counterexample, right? So this check is done by a SAT solver. So that is what's called a SAT solver. SAT stands for satisfiability. Does this make sense to you?
Yeah. So if SAT like instance is unsatisfiable, then verification will always be successful.
No, so that will mean, so basically, yeah, it will say that this particular assertion at least is successful. So when you have this one assertion situation, it means that, okay, it couldn't find a counterexample to this assertion. So it might print verification successful, or you might have, say, unwinding assertions and that doesn't hold, and then that will print verification is unsuccessful, right?
Okay.
Yeah. So yeah, but you basically have the intuition you have is correct. Okay, any other questions? So, I mean, I'm running really late, but can we extend this to say 6:30? Is that okay with both of you? If you have anything, you're free to go. With like, I'll do these things sometime else. That's also fine. Like, just let me know. Is it okay for you?
Yeah, for me it is okay.
And so this was who was this? Okay, so is it,
Siddharth.
yeah,
Yeah, for me also it's okay.
okay, so Siddhant, yeah. Okay, so then if it's okay, then I guess I can do this now. So if there's no other questions, then I'll go to this buggy merge sort and see if we can go over one of its traces, right? How do I actually do this? So let me try to go full screen view over here. That doesn't help much. I need to at least see the most of the program in one place. Okay. Yeah. This will have to do, I guess. Right. Yeah. All right. So now let's so we are going to do basically what Siddhant had shared previously, but we're just going to add a bunch of other extra these things, extra flags, mostly for trace printing. So we're going to let it automatically figure out how long it needs to unwind. So it's going to unwind and check and unwind and check and unwind and check, and eventually if it finds something that's good, otherwise it will not, and then over here we're going to set merge sort, and n is going to be 4. We don't have any k anymore. Okay. All right, I'll have, so okay. Same problem, like same thing that Siddhant was having. So what I'll do is, instead of having some non-date and so on, I'll just define this array explicitly as 5432. Okay. that will just make it so that the values we have to deal with are not very pathological or very huge or anything like that. So yeah, so verification failed. Let's pass this to less so that we can go through it. So if you look at it, firstly, it's actually, it has unwound this multiple different loops a number of times, right? It has unwound some recursions a number of times. So it's done some amounts of unwinding to find this particular counter example. So let's just go over what this counter example is, and let's see if from this counter example we can sort of understand like where the bug is happening and why it's happening. Of course, I mean, you probably have looked at this program. If you have, then you probably know where the bug is happening and you understand why the bug is happening. But let's not do that first. Let's instead look at the counter example first and try to reconstruct our understanding of the bug from there. So yeah, so let's go down this. So okay, first of all, it's in main. So in main, a bunch of things is happening. It's going to, like, I've added some extra print statements and so on, and then it's going to call merge sort. So I'm going to go like skip all of these parts in the trace before the call of the merge sort, right? Because I mean, probably the bug is not there, right? So that is not really important for us to manually inspect. Yeah, so now we're calling merge sort. So we're calling merge sort, and we're calling it with 0 and 3. So let's write a few things down just to keep track of things. So we have two arrays over here and A, right? Okay, actually let's do it the other way around. We have A and we have an aux, and A is initially 5, 4, 3, 2. So we have 5, 4, 3, 2, right? And now what we're doing, and this is going to be a stack. So now where we are in is we are in a call of merge sort with 0 and 3, right? So I'm going to omit this A because the A is there in every call. Like A is just the same thing for every call, right? So we're basically calling merge sort on this entire thing. So that will send us to line number 37. Yeah, so 37 in main. So let's wait until it skips to line 20. Yeah. So okay, so these three things in line 37 is just setting some L and R and so on. So just copying out your like your local variables to like your actual arguments to your formal arguments and so on. So then you go to this line 20 over here and it sets your M. So it's going to set M to 1. So over here, we are going to have M equal to 1, right? Then it's immediately going to do this other function call, right? Because R less than equal to L doesn't hold. So it's going to do this other function call. And this is going to be with L and M, right? So we add something else to the stack. And this function call is with 0 and 1, right? So 0 and 1 would mean that we have 0, 1. And again, we're going to calculate this M over here. So again, we're going to calculate this M over here. So let's skip this, setting this R and L and all we're skipping, but now we're going back at line number 20. So in line number 20, we are now at line number 20 inside this particular call. So this call over here. And there we are setting M equal to 0. So M is 0, L is 0, R is 1. And now we are calling merge sort for 0 and 0, right? So we are calling, so M was 0, merge sort 0, 0. That's this function called merge sort 0, 0 that's happening. So again, bunch of pointless assignments. But what it does is basically it assigns L, R, and M, all of them to 0, and it calculates M to 0 again, like you would expect. But then it returns, right? Because it says that R is less than equal to L, so it returns from over here. So immediately after calling this, it returns, and actually it doesn't do any change to the array, right? So now we are in this situation. So if you remember in A11, we were previously at like line 22. So we were at line, so let me just mark the line number. In both of these, we were at line number 22. So now, sorry, in merge at 0, 1, this previous call over here. So now it is going to call the next one from inside over here. So in line 22, we call this one. Now it's going to make this call, and this is going to be with 1 and 1, right? Because m was 0. So actually, let's do it this way. Sorry. So let's say that this is going to be our L, M, R, and line. So line 22. Now we have moved on to line 23 over here. So this guy M was 1, right? So it was 0, 1, 3, and this is 0, 0, 1, right?
I think it was 0, 1, and 2.
No, this one is 3, right?
Oh yeah, sorry.
Let's just, okay, do you want to go up and check, or?
Yeah, I think it's 3, sorry, yeah.
Yeah, I also think it's 3. I think it's, yeah. I mean, I wrote the only, I didn't write the M over here. LNR I wrote over here itself, right? So like LNR I wrote over here as well. Okay, so we're in line number 23 over here in this one, and we do this merge sort A11 call, right? So we'll again call merge sort 1, 1, and this is this call, right? Because it is M plus 1 and R. So this is 1, 1, right? So then L, R are all 1. So it calculates M as before. So let's just skip until M equal to 1. So yeah, it calculates M equal to 1, and then it returns immediately. So let's again erase this. Right? So now we have, so now we are inside of this particular call that we have done 22, 23, and now we're in merge. So we call merge with 0, 0, 1, right? So we call merge with 0, 0, 1. So let's see what happens when we go inside merge. So we jump to line number 24. Okay, so we're still in line number 24 where, yeah, we are still doing these, we are still passing the arguments to merge. And yeah, then we jump to line 9 when, we are in this first line of merge. So again, we initialize I, J, and K to 0 because it will be initialized to something. So now we are inside line 10, right? So in line 10, we're doing this loop. So we are now doing this particular loop, right? So in line 10, the first thing that we do is we set I to M plus 1. So it's I is going to be the 1, right? So I currently, so merge 0, 0, 1. So I is currently going to be over here. So let's say, let's use this guy here. So let's say this is I right now. And then it's going to execute this particular statement, right? So it's going to say, aux of 0 is going to be 5, right? So it's going to take I minus 1 thing. So it's going to take this one and it's going to put it into aux of 0, right? So we have basically this situation going on, and we get aux of 0 is equal to 5. That makes sense. Now we do I minus minus, so I is going to become 0. So now I is going to go up over there. Sorry. I is going to go over there. Now, if I is now 0, then immediately I greater than L is actually failing, right? Because L was 0. So this fails and this loop has ended. So now we set J equal to M. So let me erase all of this I things. And J is going to be equal to M. So again, M is again 0. So J is over here. And then what we're doing is we're taking this index. So this is R plus M minus J. What this will do is that, so okay, in this particular case, this index evaluates to 1, right? So this way. So it's going to put into this particular position because that's where the index evaluates to jth thing. So it's going to do this sort of a copy, right? And I mean, immediately this should sort of give you, like, this should smell of fish in some sense, right? Because what we are supposed to do in merge sort is copy various parts of the array to different positions, like to two different positions in the aux, and then merge them, right? And nowhere in our sort should we ever need to sort of duplicate an element inside of a second array, right? So this does, smell, but let's assume somebody else wrote this code, and let's just say that we're really giving them the benefit of the doubt, and maybe this is correct logic. Let's just go on and see what happens. Spoiler alert, it's not, when we know that, but so yeah, so then we do j is equal to j plus 1, so j goes over there, j goes over there, and then again this loop will terminate, right? Because j less than r is now not satisfied, so we've done this one copy over here, right? Now when we do j minus 1, it's just going to say j equal to 0. So yeah, so wait, okay, so I think I skipped out a bunch of things, right? So j plus 1, and then we time it out of the loop, right? Yeah, so now we come to line number 12. So we are in line number 12, and we start with k equal to l. So k is going to initially be 0, right? So because our l is 0, this is our l value over here, that is 0. So k is initially going to be 0. K is over here, and j, remember, was actually 1, right? So we still have j sitting over here where j is 1, right? So now what we're doing is we're doing this check and then going to execute one of these two statements, right? So this is a bit hard to read because the trace printout essentially skips a bunch of things and shows a bunch of things in weird orders. But if you look at these two things, this is the j minus minus that's happening. So we know that we are here, and this says that as well. So we're in line 16. So it says that we are here. So we know that else got executed, right? And that makes sense because if you look at I, so okay, I should probably also say what I was. So I's last particular assignment was 0, right? So I is sitting over here. So yeah, so this makes sense because aux I is this, and this guy is not less than this. So 5 is not less than 4. So you're going to go into the else case, and you're going to copy the j minus minus thing back, right? Now j minus minus means that copy the jth thing and then decrement this, right? So technically what we should get is, what we should see is the copy first and then the decrement. But because of the way this is getting parsed and processed, I think what's happening is that j is being copied to an internal temporary variable. Like look at this tmp post $0 thing. So it's showing the j minus minus first and setting j to 0, and then it's showing the copy, right? But I mean, we can sort of understand what's going on here. At the end of the day, what's going on here is that you're going to copy this guy, right? So so actually you're not even going to go do it that way. You're going to copy it over there, and then you're going to do j minus minus. Sorry, the j was, right. I'm sorry, I got really confused there for a moment. Yeah, so we're not copying it into the aux, we're copying it into A, right? So we're copying from aux into A. So the arrow should be in the opposite direction. So so what we're doing is we're taking this position and we are copying things over to 0, right? So we're copying from j to here, and then we're going to set j back. So this copy doesn't really do anything because 5 doesn't change. And then we do j minus minus, so j goes over there, right? So again, we go to line 12. So we are going the next iteration of the loop. Then we do k equal to k plus 1. So the k moves from here to there. And again, we check whether, aux I is less than aux j. And in this case, they're all the same. So this is not going to trigger, this is going to trigger, and we're going to again come to the j minus minus case. So then we again do j equal to j minus 1. So j now becomes -1, which is going to be somewhere over here, let's say. And then we copy whatever was in the previous position that j was in. So let's say the j was here, and we copy that to there, right? So what we get is 5 over here. So again, we again feel like something has gone wrong, right? Okay, so after that we do k equal to k plus 1, the loop exits, and we return from the merge. But we feel like something has gone wrong, right? Because what merge was supposed to do was it was supposed to take something that is stored between this and this and merge them, right? So it's supposed to be like, okay, this part is sorted, this part is sorted, let's assume that. Then let's just merge these two things, right? Merge these two things into a combined sorted array. But if you remember, this was previously 5, 4, and now this has become 5, 5. So that is not correct behavior, right? So we already see that there is some bug over here. And that bug, as we suspected, it still makes sense to say it is originating from here, right? But let's continue with the trace, and I'm going to go into that much amount of detail anymore. But the same sort of process happens for the other end as well. So okay, so this particular merge returns, once your merge returns, this merge sort returns as well, right? So this goes to line number 23 now, and you have basically a symmetric copy of this entire situation going on again, right? So, okay, do you want me to go over this trace once more, because it's just like the same sort of a thing, or is it fine? Okay. Yeah. So I think you can like look at it on your own, or yeah. But basically the same sort of a thing happens, and what you end up getting is, I think, 3, 3 at the end of this, right? So now you have 5, 5. Sorry, okay, over there and over here as well. So at the end of that, you get 5, 5 and 3, 3. If I think that's what you get. So then let's skip all the way up until the function return from this one, and right. So okay, so yeah, so we're back into main over there. So this is the last like final merge over here. Yeah. So this is the final merge. This is 0, 1, and 3. So like 0, 1 being merged with 2 to 3, right? So if you look at this again, what happens is that we have one part of the copy. So let me just edit some of this extra gray stuff. So again, we have one part of the copy where, so yeah, line number 10. So we are copying aux 1 to 5. So this guy becomes 5, and then aux 0 also is becoming 5. So we are copying 5 to both of these over here. But then when we come to the second loop, we'll see like very explicitly what the error is. So see, now what we're supposed to do is we're supposed to copy this guy to this part, right? But what we see is that aux 3 is actually going to become 5. So aux 3 is going to become 5, and then aux 3 is going to become 5. And then aux 2 is going to remain 3. Right? So we see this sort of a situation. Right? And then notice that like they're sort of in a wrong order as well. Right? So aux 3 is going to now be 5, and aux 2 is going to be in 3. And now when you go over the merge, remember that what we're doing is we're taking j like j is going to reduce in this direction and I is going to increase in this direction, right? So when we're copying the aux, what we're assuming is that like this is going to be sorted in this direction and this is going to be sorted increasing in this direction, right? But the opposite has happened. And that is because in the copy we have made a wrong indexing, right? So we can sort of figure out that this is the bug by looking at the trace. So at least is the spirit of like how you look at the trace and find the bug more or less clear?
Yeah.
Yeah. Okay. So yeah. Yeah. So basically, this is what I had. I have some few short things in this, unless you guys want to talk about anything. So one of the things is that this actually, so far, all of the specifications or all of the properties that we wanted to check, we have specified explicitly, right? So we have added very specific asserts, right? Also note that in this trace actually goes on for a long time. Even after the merge sort finishes, it actually goes through the print loop and goes into the assert loop and stops when this particular assert like violates. Just pointing that out. But in any case, whatever property that we have proven up until now, we have proven like by specifying particular asserts, right? So right now, the only way of specifying properties that we have seen is by asserts. But what CBMC actually has is this thing called an instrumentation front end, which will let you do a bunch of checks, like which will automatically put a bunch of asserts corresponding to certain checks for you, right? So for example, it can put asserts corresponding to array bound checks automatically, and similarly pointed checks, it can put asserts corresponding to that automatically. So you have that, and you have a bunch of things that can automatically put asserts for. So memory leaks, division by zeros, signed overflows, such things, right? So how this works is that basically there is a front end to this CBMC tool, which does something called static analysis or abstract interpretation, and figures out what asserts you need to sort of prove that bounds violation doesn't happen in this particular program, or pointer violation doesn't happen in this program, and so on. And it will smartly put in those asserts, but it doesn't verify those asserts. CBMC then verifies those asserts by taking longer and longer paths, that whole entire thing. So just a very short program to demonstrate that. So if I look at this properties.c, so we just have a static allocated buffer and a dynamically allocated buffer, and then we are copying back and forth, right? And I've made the sizes of those two buffers variable, and if those sizes don't match, we'll get various kinds of errors. So by default, if you don't pass anything, so let's say that, let's make the sizes different. So let's make m less, right? So by default, if you don't pass anything and you go to say this properties.c, it's going to say give you verification successful. So you need to pass the specific checks that you want to do. So let's say that we want to do a bounds check, right? So what bounds check will do is it will check that the indices accessing the static buffer are always going to be within their bounds. So we're going to add bounds check, right? So this gives us verification successful, right? Because see, when we are so when n is 4 and m is 3, then the static buffer is larger, right? So when we're copying into the dynamic buffer, we are making an out of bounds access for the dynamic buffer. But for the static buffer over here, we're always making inbound accesses, right? So, but if we flip this around, so let's say that we make m4. So now the dynamic buffer is larger. So then when we copy back from the dynamic buffer into the static buffer, this one will become an out of bounds access, right? So, and when we check this, and yeah, it just says exactly that, and it gives us a long trace for that. So yeah, it says that in line 18 we have a violation. So let me just disable the trace printing for now. Yeah, right. So similarly, what we can do is we can do a pointers check. So pointer will basically check whether you have whether you're dereferencing a bad pointer, right? A null pointer or a pointer that you haven't obtained via malloc and so on. So again, this is successful, and look at the number of checks that it does. Like it checks whether there's a differential like whether it's a dereference failure because of invalid pointer, or because it's a pointer that is already delocated, or if it's a dead object, or if it's a pointer outside dynamic object bounds, and bunch of other related checks that it's doing related to sort of pointer dereferencing. And all of those checks are successful. Like none of those checks actually violate. So it says that, okay, verification successful. And that is again because in this case, the dynamic, we've set the dynamic buffer to be bigger than the static buffer. So no pointer dereferencing happens. But if we do it the other way down, yeah, it will now fail. So this particular thing is failing. So it's in line 14. Pointer is outside dynamic object bounds, right? That's failing. So we can combine those two things and say, yeah, so now the bounds check is happening fine. But if we again make this 4 and make this 3, then it fails because there's in line 18 there's a upper bound check that is failing in line 18, right? So we can combine those things. Another one that you can like that I will show is basically you can check whether, so if I comment out this line, so we comment out this line, you can check whether there's a memory. So let's keep those things. Yeah, so we can add this thing called memory leak, I think. Yeah, memory leak check. So we can add, right? And let's make these guys the same. Right, and now this fails. This dynamically allocated memory is never freed. And it doesn't give you a line number, because if you think about it with respect to memory leak, a line number doesn't really make sense. I mean, you would hope that it would give you the line number of where you allocated the memory or what. But I mean, it doesn't really make sense because it points to an absence of a free statement. And the free statement could be anywhere. It can't really suggest to you where you should put your free statement. But it basically says that there is a memory leak that is happening over here, right? And it can give you a trace for that as well. So from the trace you can guess as to like why the memory leak is happening. And basically, so I've not made a pretty trace, but you can go over this and see that it's giving you a trace where an execution where the memory leak happens. So now if I remove this comment, we should finally get a verification successful. Yeah, okay. So yeah, so this is all I had. Any questions? Are you guys there?
Yes.
I'm sorry for taking so long. Yeah. So any questions, or is it okay? Hello.
Yeah, no questions, I think.
No question.
Okay. Okay. So yeah, so that is basically all I had. Sir has asked to send out something where, like an assignment sort of a thing, where you have to try to implement a binary search and see if, like, introduce some bug and then verify and then fix it and that sort of a thing. So we will basically send out some announcement with respect to that. Okay.
Yeah.
Yeah. Okay. All right. So I'm not going to keep you any longer because it's already gone on for too long. Yeah. Bye.
Okay. Thank you.
Yeah. Bye.
Thanks.